All right, so let's open this topic one video by discussing implicit differentiation by first talking about x and y and how they're similar and how they are different. Um, if you watched the intro video, you heard me say that we know x and y just from what we've been learning, probably actually since Algebra 1, maybe even, that x is our independent variable and y is our dependent variable. So x is kind of the standalone variable. We input values into it kind of however we want. And what we input for x does affect y, but we can choose anything we want for x. Y is a dependent variable because everything that y is dependent on what x is. And I feel like I'm talking in philosophical terms, like I feel, but I'm just talking about x and y here. So, as I said in the intro, I don't know if I'm making relationship advice or if there's like spiritual advice in there or what. But anyway, x is the standalone variable. Y is completely everything about it involves something about what x is. And so when we derive those variables, we need to treat them differently. We can't treat them the same. To show you what I mean, take a look at these two examples so we can compare them. On the left, I have the function y equals x squared, which is something that we've derived before. It's one of the most basic functions that we've looked at. You know, it's just a power function. Then on the right, we have y squared equals x. And the question is, how does deriving this, how should it look similar and how should it look different? So let's start with the one that we know, y equals x squared. Well, we know that this is just a power function, and we say that y, we're looking for the derivative of y, so dy dx, should equal, swing that 2 to the front, drop it down by 1 power, and it's just 2x. So the derivative of y with respect to x is just 2x. Just kind of moving down that ladder, right? The ladder of differentiation. On the right-hand side, we're still going to be able to use the rules that we know about power rules and things like that. But let's say that I just came along and said, oh, let's just derive this the way that I want to. Let's just do 2y equals, well, what are we going to do? Just 1? 2y equals 1. Well, if we're moving down the ladder of differentiation, where'd the dy dx go? Like, something's missing here, right? Like, here we're moving down the ladder. Here's the function. Then we derive, we move to the next level function, which is like y prime. Well, over here on the right, something just looks wrong. It looks like we've changed the function, but it doesn't really look like we derived it. And that's because we didn't. We actually left out an important part. Because y is not, here I need to erase this now. I want to erase everything, just our differentiation. Y is not just a variable. Y is a function. And anytime we derive it, we need to treat it as a whole function. And so that should involve dy dx. So if I'm going to take the power rule and say what's the derivative of y squared, the answer is actually more like a chain rule problem. The outside function is something squared. The inside function is y, because y is a function, right? It's not just a variable, it is a function. So it's a chain rule. Derivative of the outside function is just 2y. That part sorry, I erased and that is scary looking. Let's make that a lot smaller. Let's see. Oh, that's better. Okay. The derivative of the outside function is just 2y. We said that. The derivative of the inside function is just dy dx, right? That's what we've been calling the derivative of y all this time without really realizing it. The derivative of y is dy dx. So the outside function is 2y times the inside function is just dy dx. So this is like the chain rule in a regular looking problem, right? It doesn't look like we have an inside and outside function, but it is. And on the right-hand side, we have the derivative of x, which is actually 1, right? Because it's x to the first power. Swing the 1 to the front, and then it goes down to 0. This is the answer, although it looks a little bit funny like this, because usually we want to have our answer in the form just dy dx equals something. But I can do that. I can rewrite it just with our knowledge of algebra. We can take actually this 2y and divide it to the other side. So I'll end up with the derivative of y with respect to x is 1 over 2y. Now that looks more like a derivative, right? We actually have dy dx equals 1 over 2y. And if we wanted to rewrite this in terms of x, we could even solve for y. Like we could go back to the original problem, let's use the blue, and we could say, well, y is equal to plus or minus the square root of x, right? And we could actually take that plus or minus the square root of x and we could plug it in for y if we wanted to. 1 over 2 plus or minus 2 root x. We could do that. We could rewrite it. We don't necessarily need to unless we're asked. But we can do anything we need to do to change this function as long as we use the chain rule when we derive it, we're going to get a correct representation of the derivative. All right, just in case that's still a little muddled, because I know I'm throwing kind of a lot of brand new information at you, let's look at another example that maybe is a little bit more complicated and take it slowly, one step at a time. But we're going to do that in the next topic video. So you can stop there, stop your notes. You can write topic 2, and we'll start over with a different example, and we'll see how this difference between x and y is going to affect how we derive. And this is, by the way, I haven't actually said what is implicit differentiation. Implicit differentiation means that we are implying through our differentiation that y is a function, not just a variable. That's implicit differentiation. Looks at y, it implies that y is a function, not just a variable. All right, that is topic 1. Let's do another example, kind of lay it out and work through it slowly, step by step, in topic 2.